All right, so we have about a week to go, right? Well, a little more, but we'll see what happens. Week and a half. Yeah, but I think Monday is the last week. Monday is 20th, I believe. And then I'll give you the test on the 21st, sometimes in the evening. Then you have the whole day. Will probably be a little over 24 hours. I don't really care. So definitely we won't have class the last day of classes. You're doing your test. And Monday, we'll see. We'll see where we stand. The theory is pretty much done. As I said, I really want to touch a little bit on the how you deal with the inertia matrix, but it's really not huge material, important material. I mean, it is important, but it's not introducing anything major. So this is the time to try to digest what we've done. And even though this class has no homeworks, I hope it's clear that at this point, when I don't finish problems, that's your homeworks. You better go back and finish them or redo them from scratch. So this is the one that we were solving the other day. So let's try to continue. I hope I've written down everything we got. I actually went back and watched the video to make sure that I was going to be consistent. So no friction between this first rigid body of mass capital M and the ground, and then which is of course an inertial reference frame, and then there is a uniform disk of mass little m rolling on it. So they're both free to move. We know we have 2 degrees of freedom, x and theta, and this is what we done last time. We set up all the the reference frames, ground. We call this A, even though it's not really rotating with respect to the ground, but has a different origin, of course. And then we called B the reference frame that is the plane perpendicular to the board through OQ or OP, and then the reference frame of the disk is C. And we found the acceleration. So we started doing kinematics. We're dealing with rigid bodies. So there's 2 things you do: acceleration of center of mass and angular momentum with respect to the center of mass. You start from those. There's no escape. So we found the acceleration of the center of mass of the disk, which I called A sub little m, which is this expression here. I didn't bother reorganizing it or making it consistent in terms of coordinate system unless I need it. I don't see why I should do it. Same for center of mass of big M, which again, we don't know exactly what it is. We know it's along these axes of symmetry. Oh, there is gravity, of course. There was something missing here. We don't know which height. We don't really care. That object is just translating, which means all points have same velocities and same accelerations. By applying the rolling condition and assuming that all initial conditions are at 0, we derive the relationship between phi and theta. Fine. We discussed that the angular momentum for the only rigid body that is rotating, which is the disk, is this expression here. The moment of inertia about the z-axis, which is the axis perpendicular to the board, times the angular velocity of that object, which is phi dot minus theta dot uz. And then we started with the laws of Euler. We did the free body diagrams. For the disk, we have, of course, gravity, and then we have some normal reaction to the track, and then some static friction that allows it to roll. There must be static friction, otherwise there's no roll. And then we go to the other object, which has also its own gravity force, some reaction from the ground. The fact that I put it here is just because I didn't want to overlap the 2, but it doesn't really mean that it's applied at that point. So that we call it NG. And then, remember, if you call this N and F sub F, this is minus N and minus F sub F. Otherwise, it's a major error because you're not respecting the third principle of Newton. So first Euler law tells me that on first mass, this is what I have. Mass times the acceleration of the center of mass for the disk is mg plus n plus F sub F. I don't know n, I don't know F sub F. For the second rigid body, I have something similar. Capital M, acceleration of its center of mass. mg, I don't know why I called this minus, that's plus, and n sub g, which is this reaction from the ground, which is frictionless, and the opposite force is minus n minus F sub F. And those are 2 vector equations in the plane. Then we said, okay, for the second object, the disk, I also can apply the second law of Euler, which is in the general form is given by this expression. ddt in G of HQG is MQ minus this cross product, knowing that we can transfer the H bar G, which is up here, to this point Q by this transformation, if you like, or this relationship. And we were stuck at some point figuring out which point to pick. We picked one, but there was something strange going on, so we'll go back to that in a second. I hope it's clear why these equations may not be enough. Is it clear to everybody why they're not enough? Because I have three vectors that are unknown, 1, 2, and 3, right? And if you think component by component, that means actually 6 unknowns in the plane. They're vectors. And so these are two equations, right? Because this is a vector equation in the plane. This is 2, 4. This is going to be 1 only, because everything you do in the plane, cross product, is going to be perpendicular to that plane. So whatever comes out of this equation here, second Euler law, is going to be on the z-axis. So that's a fifth equation. That's not enough. I actually need how many more? Is it 1 really sufficient? Because the point is I want to find differential equations in terms of x and theta. So I don't want to solve for those unknowns. I want to get rid of them. So in principle, you want 1 more equation, right? And that's exactly what happened. If you go back to that exercise here, I think that's exactly what happened here with the wedge and the block. By doing the free body diagrams of the two, it wasn't really enough. We needed to look at the system in its entirety, right? And that's what we can do here as well, and we'll do it. So, okay. So 5 equations, 6 unknowns, if you put it that way. So I need something else. And the free body diagram of the entire system, which we'll do, that is another 2 equations, because it's another vector equation in the plane. So then now I have 7. I can play with them and eliminate the unknowns. And please understand how painful this is. This is a simple problem, relatively simple problem, and it's getting huge in terms of calculations because of all these unknowns that you have to eliminate. So as I said last time, this is probably one of those cases where Lagrange's equations may be a good idea. But either way, you get to a solution. So if you apply the principles right. So this point here that we need to pick. We said, okay, if I want to use this expression, it would be nice to have all the unknown forces, and I'm looking at the disk. So basically these 2 forces here to go away in the second law of Euler. And that means picking that point Q. Now since it's rolling, point Q has really different meanings. We've done it for the case of an inclined plane, right? And I think there was this disk rolling here. We did it in different ways, where Q is part of the disk, where Q is actually this point here that goes down the incline, and it's always below the center of the disk. We've done it in different ways. As long as you substitute the correct accelerations and velocities here, you'll get the correct result. So the suggestion was, let's use Q on the disk. Not sure if that's the best, but let's use that. So that would be Q on reference frame, if you like, C, right? And we said, okay, I want, for that point, I will need the acceleration, well, velocity and acceleration with respect to the ground. So the roll condition tells me that the velocity of point Q, seen as part of A, which is capital M, in some reference frame X, any, needs to be equal to the velocity of point Q, the point that now belongs to C, the disk, in the same X reference frame. You can pick whatever you want for X, whatever is convenient for you. And in deriving these, we said, okay, let's pick A, because if I put here A and A, this goes to 0, so that's pretty nice. I get VQC in A is 0, and that allowed me to find this relationship. But now I'm looking at the ground, so I'm going to do this. I'm going to say with respect to the ground, because this is my unknown right here, right? I don't have the other subscript C, but if I am using Q as part of C, that's what I'm looking for. And I know that the velocity of any point on A, doesn't matter which point you pick because it's only translating, that's x dot Ex. Do we agree with this? we also know that the acceleration of any point, keep breaking this, on A with respect to the ground is x double dot Ex, because it's only translating. But when we said, okay, this is fine, I can say that this is the velocity of the point Q on the disk, it doesn't sound too strange. But then we said, this sounds strange. If I say that the acceleration of point Q as part of the disk, so if I say that also this is equal to A Q part of C in G, we were not 100% sure about this, right? Do you remember? We were right there. Okay, so what do you think is happening here? I'm telling you, this is not what happens. Cannot be. First of all, why cannot this be? If the acceleration of that point Q as part of the disk is the same as Q part of M, it's a hinge. They're stuck together. They're moving the same exact way in time, right? Two points can have the same velocity at a certain instant, but then have different accelerations and go completely separate ways, which is what happens when you roll. The point on C, which is the contact now, it will not be the contact at the next instant in time. T plus epsilon is not the contact anymore. That point has gone somewhere else, while all the points for capital M are going just straight back or forward, I don't know, but they're translating horizontally. So this really is not, I don't think it's something we can assume. Do we agree with that? Would you have fallen for this trick? Would you have told me that this was going to be x double dot Ex? Because there is a temptation here, because I agree with this. I can say that VQ as part of C with respect to the ground is x double dot Ex. The only thing this is valid when? Right now. That's it. This is instantaneous. Remember we said this is the instantaneous point of contact. Instantaneous point of contact. So if x dot is, I don't know, 1 meter per second, so the value, you stick it in there and it's in this direction at that instant in time for the point Q that is on C, but it's not true that this is the function that gives you velocity of Q as part of C at all times. It's just you're taking a picture. Right there, it's true, but then it's not. Is this clear? Try to make the parallel in your mind with the simple case where we're just rolling on a flat surface. Well, I was screaming. Now that it's quiet, I don't need to scream anymore. So I think it was clear here that this point on the disk actually had an acceleration in this direction. I think we demonstrated that. So it will go away. It will not maintain zero velocity, because if it maintains zero velocity, then it's a hinge. It's not going anywhere. It's just rotating about this point. So don't fall for these tricks. You cannot do this. This is only true right now. But the acceleration of that point, Q, if you want to pick Q on C, it's something else. And you need to find it. So you can stick this in there. The velocity of Q in G, it is this right now. You can put it in there in that expression to find HQG. But you need to do something else to find AQG. Okay? Now you guys tell me what I need to do to find AQG. If you really want to do it with that point, which is probably not the best idea. How would you find AQ, where Q, again, it's a point on the disk with respect to the ground? How do you find this? Look at what I have. This is, if you want, this is the same as saying the acceleration of point P, right? Because P is the center of mass of the disk. Yep, yeah, see, this is what it should happen. Now I remember, there's something relating those 2 points. That's all you need to to know that there is something relating Q and P because they are on the same rigid body. Then if you remember the formula, fine. If you don't, you have a book.
Yeah, it was something like AP minus this
Yeah,
equals,
yeah.
and it was like the
AQ,
the rotational acceleration.
yeah,
And it was like
minus AP in G is equal to alpha C with respect to the ground cross with RQ minus RP. And again, this would be the same as R bar for the disk, plus, what is here? Omega CG. What goes here?
omega. Yeah.
Is another omega?
Yeah. Plus.
Do you really want to do it this way? No, this is, yeah, I agree, this would be the way. So AQ, you just have an equal here. Yeah, plus all this stuff here. And omega, well, this we know what it is. Phi dot minus theta dot uz. This will be just phi double dot minus theta double dot uz. And then figure out all these cross products. You can do it that way. We've done it before. It's another additional pain in the neck to do it that way. I only need a point that is right there, right now, so that all the moments with respect to the point for the unknown forces go away. So I think that probably I want to pick these. It's the same actual point. It will give me the same result in terms of moment, but its velocity and accelerations are a lot easier because the velocity of Q, as seen belonging to A in G, is x dot Ex. For this point, I know that I can do this, right? This is true, isn't it? It's the same, they are overlapping, but they're just behaving in a different way. But all I care about is that they are physically in 3D Euclidean space in the same location so that MQ doesn't give me anything that has to do with N and Eb sub F, right? So I think I would do that. Do you like it? And of course things will be different because this will be the same, but then you have a different acceleration, right? Do you agree or not? Okay, do we need to do it? Do we need to go through the calculations here? So we can start it if you want. I really want to do the free body diagram of the entire system and then maybe see how this would be done with Lagrange's equation. So, well, the first thing I have to do is HQ with respect to G is H bar with respect to G, which is this expression here, IZZ bar phi dot minus theta dot U Z, and then I have all those things. What is RQ minus R bar? What is it?
Minus that again.
Is it? Minus L ER. Is that ER? Yeah. Okay, plus that cross with M. I said that this was x dot Ex. Please tell me that you have the velocity of the center of mass somewhere. Because I think I have it actually. Do I? I refuse to do it again.
It's x dot Ex.
Yeah.
Plus theta dot times capital R minus small r e theta.
That's it? So this term plus this term was what we found for the velocity of the center of mass. I believe you. I have different coordinate systems, of course, in my notes. So, okay. If this is true, and again, you go back and redo this from scratch, I think it's a good idea. Well, these will go away. So you keep doing your calculations here. IZZ bar, which, by the way, you can call just I if you want. That's the only I that is involved here. UZ, what am I left with? Minus LER cross M minus minus plus theta dot. Okay. Doesn't look too bad. I, Z, Z. So do I know where I'm going with this? What do you guys expect? What is this going to be? A vector pointing which way? ER crossed with E theta is what? EZ? So that's plus ML theta dot R minus little r EZ. These guys are one the opposite of the other, so you can just put a minus here if you want and have UZ here. And that makes sense. As I told you, that equation will only give me one direction, the Z one. So if you get another component here which is in the plane, there's something is wrong because you're doing cross products of vectors that are all in the same plane. It cannot be. Okay, so you can collapse all these together and you get something. And I never bothered replacing phi dot with that expression. Maybe I could do it. It's up to you. IZZ bar. Yeah, let's do it. So this becomes a theta dot minus another theta dot here. And then I have a minus ML theta dot R minus little r. Everything is along UZ. Okay, that's my, no? Yes? That should be my H with respect to Q, and it does dimensionally make sense. This has the dimensions of mass length squared, mass length, another length, mass length squared. So remember what you are doing here would be the parallel axis theorem, even though we don't really call it that way. But that's what you're doing. You're moving H to another axis. Okay, and then you will have to take the rate of change of these in G. Let's do MQ first. So let me write what this is up here. Theta dot R minus R, and this is all on UZ. Okay. What is MQ? Should be pretty easy, right? I picked it so that those forces go away, so what is it? F sub F, N, I don't care. So cross MG. What goes in here? What do you think? Why am I using little, what is L, by the way? Why am I using L? I don't see any L. Is there, right, that's little r, right? I think we're just dragging pieces from other problems. Yeah. Okay. Isn't that L minus L ER that goes in here? I mean, what you're doing is the moment of this vector with respect to this point. So you're basically looking at this vector here that goes from Q to the center of mass, and that's minus L ER. So mg is also mg minus EY, right? So how about this? I'm going to change this sign here. What is ER cross? So in the end, I have L. Yeah, that's keep doing it. Yeah, I know.
There's a minus in the HQ, minus MR theta in the above equation.
This?
Yeah, it's a minus.
Where?
That's what I was thinking. 'Cause there's
This?
no E at the end.
This was a minus?
Yeah.
Thank you. Believe you.
It's
I-
EC and EC is minus UC.
I erased it. Oh, yeah, yes. See, I need a bigger board. Definitely a bigger board, but yeah, too late. Okay, so all the constants are there. What I'm looking at is the cross product of ER and EY. ER is pointing this way, and EY is pointing this way. And what's the vector between them?
Sine theta easy.
Is it? this angle is pi over 2 plus theta, correct? Is it? No, it's pi minus theta, I'm sorry. Or the opposite, I was looking at the wrong vector. It's pi minus theta, right? Okay? So I'm doing the cross product of ER and EY. Looks like it's coming out of the board, right? So it's EZ, definitely a plus EZ. And there is some sine, cosine that goes in here. That's actually the sine of this angle. What is the sine? And here we go again. The sine of pi minus theta is the sine of theta, I think. Okay, so this is sine of theta. EZ. No? Yes? Yep. And by the way, EZ, UZ, they're all friends. They're all pointing the same direction, pretty much. Yeah. I mean, it needs to be that way. Otherwise, something is wrong. And then the only other term that we need to figure out here is this R bar minus RQ crossed with M. And R bar minus RQ, we had done it here. What was this? It was minus L ER, again with this L, minus R ER, right? Which is crossing MX double dot EX. Is that correct? I'm including the minus already. Or if you want, I'm looking at RQ minus R bar, which I think it was minus R ER. And so you do what we just done here again. You have what is this is RM, that's my NX double dot. This is definitely something along EZ as well. I need to figure out what it is. EX is this way. ER is still this way down here. I am doing ER cross with EX, which is, again, along EZ, but there is a minus. So I think there's a minus there. What is this angle? This is what? Pi over 2 minus theta? Cosine of theta. So the sine of this, sine of pi over 2 minus theta is the cosine of theta. Nice. I have the three pieces. Well, I will have to take the rate of change of these in G. Yeah, we can start that, but I really want to move on to Lagrange's equations. So what you need to do, this is all, well, transport theorem, right? So dt in G of HQG is also the rate of change of AQG in which reference frame? In the one where UZ is fixed, which is C, plus omega C G cross with H itself. And quite frankly, if you don't know how to do this at this point, I don't know what to say, because this is, again, taking derivatives and doing cross products. I think we're pretty tired of doing this. This rate of change will be basically ignoring UZ, just leave it alone and take the derivative of everything that changes with time, which is only theta. And here, it's okay. So in the end, when you do this, you guys go home and finish it. Do your derivatives, put it all together. This is just another equation. This is just one equation on the z direction. That's my, what did I say? It's my fifth one. Okay? That's not enough. I need more to eliminate those annoying reactions. And the one that I don't think I need this. The place where I'm going to get that equation is looking at the system as a whole, which is saying the free body diagram of the whole system here, which is looking at what force. I don't know where the center of mass of this entire system is. It will be somewhere, depending on where this object is, somewhere, say here. I'm going to have capital M plus little m G, and I'm going to have this N G. What else do I have when I look at the system? all together. That's it. All these guys are doing between themselves, it's their business. I don't care. It's internal forces. They cancel each other. And so these additional two equations that I get tell me that m plus little m, g plus ng is equal to m plus little m, acceleration. Now I'm not going to say of anything. This is the acceleration of the center of mass of the entire system. And what is this? Well, you have those two accelerations. So the acceleration of the center of mass of the entire system is little m, acceleration of the center of mass of the disk with respect to the ground, plus big M, acceleration of the center of mass of this object with respect to the ground, divided by the summation of the masses. And that's what goes in here. And of course, it will simplify with that. So it's just the numerator. And you know the gravity force. The ng is an unknown, but this is another two equations. So now you have 7. Your 6 unknowns, you can somehow, with extreme pain, get rid of them. That's why Lagrange's equations are so great, because I don't have to go through that pain. I go through different types of pains, but I think that solving a system with 6 unknowns, it's pretty bad. So again, that's why you get 24 hours, because I really don't want to give you something that takes very long, but you can tell how just two rigid bodies moving can become a big problem. Okay, so any questions about doing it the classical way? Please go back and finish all the calculations. You have the steps. You have the start for every step. The only thing you're left to do here is cross products and a few derivatives. That's it. And again, I do care that you show me you know how to get to the system of equations that are enough to eliminate unknowns and give me my final differential equation. If you don't practically do it, that's still okay. You're using the principles correctly and you're getting where you need to go. So that's important. Okay, so if you have no questions about this, how would you do Lagrange's equations? And I'll just give you the start as well, so you can finish your calculations. And I don't know if you really want to compare with what you get from solving the system of 6 unknowns. The equation is the same, d dt partial of the kinetic energy of the system with respect to qi dot minus partial of the kinetic energy with respect to qi is equal to qi, where in this case I is basically 1 and 2, or if you want, q1 is x and q2 is theta. Okay. Okay. What is t? I need to find t and q and the generalized forces. That's all I need to do here. Knowing that in here, I don't care about which forces. I don't care about n, ng, ab sub f. They're all constraint forces. This is preventing this disk from breaking into the guide. This is actually allowing you to say that there is roll. It's a constraint that you express on the velocities. And this is preventing the whole thing to just collapse and go down through the ground. So those are constraint forces. I don't care about them in Lagrange's equations. So kinetic energy is, in general, for a rigid body. Let's refresh our mind here. 1/2 mass, velocity of center of mass with respect to the inertial reference frame dotted with itself, plus 1/2. I'm sorry? No. H bar with respect to g, omega of that rigid body r with respect to g. Okay, so if I have two of them, then I sum the kinetic energies of the two. That's what you do. We're basically extending here. We're not doing more demonstrations, but we've done Lagrange's equations for a particle. We did it for systems of particles. Then we went to a rigid body. Well, when you have multiple rigid bodies, you add them together. You treat it as a system of particles, pretty much. That's what you have to do. With the difference that, again, that these Qs now, since they're rigid bodies, they actually have dimensions. Those forces can be applied in different places, while with a particle, they are only applied to the particle. Very specific location. Okay, so in this case, This is a general form. I have two rigid bodies. The first one is only translating. 1 over 2 mass. Can you just tell me what was the velocity of the center of mass of that capital M? It's x dot Ex dotted with itself. So it's x dot squared, right? Okay. Then I look at the second one. 1 over 2. Oh, I don't have velocity here. Can you tell me what the velocity was?
X dot Ex
I know.
plus theta dot times r minus r.
E theta? Okay. So what you get if you dot this with itself? Same. Well, let me rewrite it. X dot Ex plus theta dot r minus e theta. Well, let's do it one by one. I get an x dot squared, right? I see that. Then what is the dot product between Ex and e theta? This is Ex, this is e theta. You're projecting e theta on Ex if you want. That's what you're looking at when you do the dot product, and that's what? You don't want to tell me? Are you sure it's cosine theta? I believe you. Okay. Okay. Plus x dot theta dot r minus little r cosine of theta, and this is twice because I will get it from doing this other dot product here, plus the square of this last one, theta dot squared, r minus little r squared. That's my, yeah, that's what I get here. So I would have, little m mass x dot squared plus 2x dot theta dot r minus r, big R minus little r. You don't agree with the cosine of theta? We can fix it. You guys do the work. I just write. I don't want to think anymore. Doing projections and stuff like that. You're okay with that? So you will have enough time to have a separate piece of paper and do your drawings and figure out what the dot product is. So this is the translational piece of the kinetic energy for the disk. And then I have 1 over 2, h bar is right there. Allow me to just call that I because there's nothing else really. It's a constant. Phi dot minus theta dot uz, which is dotted with the angular velocity of the disk with respect to the ground, which is the same. It's right there. So how about I square this and I'm done. Make sense? So now what you will have to do for the left-hand side of this, yes, I agree, it's algebra. You have to do the partial of this expression with respect to first theta and stick it to, you have two equations, of course, here. You get two Lagrange equations, one for x and one for theta. So, for example, you start doing the partial of t with respect to x. You treat theta as a constant in your derivation, and that gives you this piece. Then you do it with respect to x dot, and then you take its time derivative, and you get that piece, and so on and so forth. If you want, we can do one, or at least start it just to see it, but I want to do the Q first. Because getting the kinetic energy, which basically means doing kinematics, and doing Q are the important parts. Then taking derivatives. It's a prerequisite for this class. So, what is Qx? Don't try to imagine what that is. Just tell me the definition of Qx. It's tough. I know it's the Lagrange, it's the generalized force that has to do with x. So there will be some partials of positions where the forces are applied with respect to x. We agree with that, right? And then usually here you have some force that is dotted with this vector. So there I'm going to have all the forces except the constraints ones that are applied to this system, dotted with the partial of the positions where those forces are applied with respect to x. And what are the forces I care about here?
Gravity.
That's it. The other ones are
Do we
constraints.
treat the system as a whole, or do we do?
Yeah, you treat it, as I said, you just treat this as if it was a system of particles. It's a system of rigid bodies, but that's what you do. You treat the whole thing together. Yep, exactly as we've done with system of particles, except now these forces here are applied in different locations. So basically this is going to be, if I look at the disk, is mg, which is dotted with the partial of the, where is mg applied, is the partial of rp, center of mass in this case, with respect to x. We'll figure out what that is, plus mg, I don't think I need these for now, dotted with the partial of, we never figured these out, right? The partial of the center of mass of the capital mass M with respect to x. But we probably don't need to figure it out completely. I don't think so. OK, mg and capital MG, it's what it is. They are along EY. Let's try to, well, let's start with this.
They're along negative EY, right?
Yeah, yep. So I know, what I'm saying is that I know how to express them. I can always do it. The other two vectors, the partials, I don't know them for now. We said something that the center of mass of this strange guide here of mass capital M is somewhere along this line, and we tell where that is with the variable x. So with respect to the ground fixed coordinate system, which, yeah, that will have some origin somewhere else, right? This will be some x ex plus some constant y, let's call it y bar, ey. I don't really care about this because when I do the partial of this vector with respect to x, I only get ex, and I like that. So what is this going to give me?
That's 0.
0. I'm fine with zeros. I don't have a problem with zeros. OK, that's one. And then I have to figure out the other one. The position of P, I think we had it. It's some x ex, right? Actually, let's start from here. Let's say that it's the position of O. So that's some x ex plus, well, I know what that is, right? Some r ey. That's a constant anyways. I don't care. Plus this vector here, which is big R minus little r er. OK? So when I start taking the partial of this with respect to x, I still get this capital Ex. This is a constant. It doesn't matter. Well, that does matter, right? Why? Does it matter? I'm asking you. Oh, to be completely thorough, if I look at the position of P with respect to the ground as the addition of the position of O and then this vector that goes from O to P, this point O, well, oh no, you're right. I picked the origin here, so I don't need that. Yeah, you're right. Thanks. So yeah, if they are, I remember I picked O of the fixed with the ground reference frame as O at time 0. So they are the same height here. So this is just xex. OK. What do I do with that ER? Does it depend on x? Yes.
Yeah.
No, I don't know. It does?
It doesn't change direction if x changes.
Theta has to change, but not if I fix theta. That's what I'm doing there. I'm doing a partial of something with respect to a variable, which means that whatever other variables are involved, I freeze them, right? So ER depends on theta, but not on x. 0. This whole thing will go in here and will give me another 0. That's fine. It means that the Lagrange equation corresponding to x will have a 0 qx. I don't see a problem with that, right? And if you think about what's going on here, if you start this system at any given initial condition and you let it go, this disk will start rolling back and forth, and the mass will start moving. What happens to the central mass of the entire system? It does oscillate vertically, but horizontally it should stay the same position, right? So I guess that equation is that's what it's going to tell me. Okay, so qx I figured it out. Fine. So you will do d dt of the partial of this with respect to x dot minus the partial of this with respect to x equals 0. That's your first equation. We like zeros, right? Okay.
Shouldn't the center of mass be changing in y direction?
In the y direction, yes. Yeah.
It's changing in x.
You mean in this direction? In x, the center of mass of the entire system. If I look at the from outside, if I look at this in its entirety, there's no force in that direction, right? The internal one's fine, but there is no force in that direction. There's only gravity reaction from the ground. So the center of mass of the system should not change x.
Yeah.
The x of the mass changes, the position of this changes, but they move in a way that the overall center of mass is always where it was, and then it's going up and down because you're exchanging potential energy with kinetic energy, but we haven't really touched that too much. But that's what is physically happening. So q theta, I need to figure that out, is the same, except I have the partials with respect to theta. Yep. Well, let's do this again. I may get a 0. Oh, it's fine if I get a 0.
Probably not.
Well, let's start from the easy one. This. That's 0, right?
Yeah.
But the other one probably not. Because RP, which I just erased, was this vector here, xex plus r minus r, capital R minus little r, e r. Okay. So if I take the partial of these with respect to theta, I don't see theta here. This goes to 0, but this depends on the angle. So to find partial of rp with respect to theta, I have to find the partial of little er with respect to theta. And I think we've done this before, at least twice, right? I need to express ER as a function of theta. So let's go here. ER is, what is ER? Is it cos theta EX minus sine theta EY? Or something like that?
I think it's sine theta minus cosine EY.
Oh, yeah. Okay. Too bad, huh? I can do the partial of this. So the partial of this is going to be a cosine of theta EX plus the sine of theta EY, which I will have to dot with, which one am I looking at? This one, mg. So I'm going to dot this with mg ey. There is a minus probably, right? So I'm dotting these with minus mg ey. And this is going to give me minus mg sine of theta. That's it. We're done. But I hope you get in the point here. In 10 minutes, the only thing that is left here is doing these partials of this equation.
R minus R.
What is it?
The R minus R, capital R.
Yeah, thank you. So, yeah, there is a minus r minus little r here, and so there is also here. And ignore that there is nothing here, but this is the final result. So this is your cubed theta. So I hope it's clear that after 10 minutes, I'm almost done. I have to take the partials of this, but this is just algebra. I don't have to go through the pain of all these moments, picking the point, and doing all those things that we've done in 2 lectures almost. With Lagrange's equations, you're getting rid of all those annoying forces. And you get the equations in much less time. Okay, we'll see you Monday.